Okay, so right now we're going over experiment 9A, and we want to see what sort of patterns there are. We had n, that was the number of harmonics, and just for the people who were doing it at home, for harmonic number, these were just the solid numbers 1 through 6. For people here, you could have chosen other harmonics because that's what it allowed you to do. We have wavelength, which could be in centimeters or meters, and frequency in hertz. The last column, I don't really know what it is, but I know that in order to find it, I took the wavelength times frequency as a product. So what is one pattern that your group saw when you looked at all of these variables put together?
We noticed that the frequencies remained pretty much the same, with little differences.
Okay, so that's this column?
Oh, sorry. It was the wavelength times the frequency.
Right.
Yes. Yeah.
Whatever that is the same number all the way through. What is another pattern your group noticed?
The frequency seemed to increase by like the same amount each time.
All right. So we know frequency increases and by same amount. Right? Did anyone get the graph for this? As the number of harmonics increases, what did your frequency graph look like? What did you guys get?
Frequency and harmonics.
Mm-hmm.
We had that being a
proportional. Yeah. All right, so I'm going to make up some numbers here. Since this is a proportional relationship, that means if it was the first harmonic, let's say your first harmonic was 20, then all my other ones would be multiples of 20. So this would go up by 20, 40, 60, 80, 100, and 120. So that it goes up the same amount each time, and it's proportional. Technically, it's not direct because you can't have a 0th harmonic, but gosh, that's close enough, right? Eventually, when we get back from April break, we'll do the equation for this, which is that if you want the nth harmonic, you would take it n times the first harmonic. But that is a future us problem. So that's a pattern. We see that as the number of harmonics increases, frequency increases. Okay, so what does wavelength do as all this is occurring?
It exponentially decreased.
And actually, I can give this number to you because all the people at home, you all had a string of the same length. Wavelength decreases because as you go up in harmonic pattern, from the first harmonic to the second harmonic, I have to fit more and more antinodes on this string. Since I have to take the same string and split it up into smaller and smaller pieces, well, that means that if I fit more harmonics on, the wavelength decreases. Actually, so everyone at home is going to have this pattern. You had 2, 1, oh gosh, 2/3, so 0.67, 0.5. Okay. Everyone at home had the same pattern for that because you all had a 1 meter length string. Okay, this is 0.4. I'm trying to do them in my head. It's a little slow. And the reason that's happening is because as the wavelength is getting smaller, it's trying to fit more and more antinodes on the same length string. So it's got to get smaller. It's trying to fit more things into the same space, right? So if you look at, let's say we compare the second harmonic to the fourth, the second harmonic has a wavelength that's this big. The fourth harmonic has a wavelength that's half of that, smaller. So one more pattern for us. That means if I graphed wavelength versus frequency, how are these two related to each other?
They have an inverse relationship.
Exactly. And this inverse relationship, their group had asked me earlier, they're like, well, which do I put on the y-axis? Which do I put on the x? It actually doesn't matter because it's an inverse relationship. So let's say I put frequency here and wavelength here. Even if I switch the axes, it still gives an inverse relationship. Now, to me, that makes sense because if I have a large wavelength, that's a low note, a low frequency. Just like if I have a large instrument, I had a low frequency. If I had a large pendulum, I had a low frequency. It's all the same thing. So if I have a large instrument, I have a large wave and I get a low frequency out of it. So all of these patterns work together, and they work together with something I haven't talked too much about. This column that we said stayed the same. This column that we said stayed the same represents something special, and I'm going to help us out with number 2. If you were stuck on number 2, the unit analysis question, this is actually what I'm trying to get out of this. I'm asking, what are the units of wavelength times frequency? So help me out. What is the unit of wavelength?
Wavelength in meters.
All right. What is the unit of frequency?
Hertz or HZ.
Hertz. All right, now a tricky one. What's the other way you can write hertz?
S to the -1.
Write hertz as inverse seconds. Either s to the -1, 1 over s. Those 3 things all mean the same thing. When you're talking about oscillations per second, oscillations doesn't have a unit. There's no like metric unit for it, just like there's no metric unit for like number of slinkies. It's just a number, so there's no unit. If I took m times 1 over s, what does that compound unit turn out to be?
Oh, m over s,
All right.
meters per second.
Exactly. And what's that a unit of?
Speed.
Bingo. So, surprise, in your lab, that 4th column that I had you calculate repeatedly, that's its wave speed. Speed is meters per second. And so when I do wavelength times frequency, I get speed back. So this is called the wave equation. And I'll put this on the big screen, like the shared screen with you for a sec. One special thing about the wave equation is that this means wavelength and frequency affect each other. So this half of the equation says that if wavelength increases, frequency decreases. A large instrument has a low frequency. Those two are inversely related. But as Jude pointed out earlier, the wave speed stays the same. Wave speed only depends on the medium that it travels through. So V is going to be the symbol for wave speed. And I'm going to switch over to the follow along slide so we can write this one down. So a lot of those patterns, the harmonic pattern, right? The wavelength pattern, trying to fit more waves on the string. We're going to come back when we talk about name of thing. We're going to come back to when we talk about standing waves in instruments. So we'll talk about like all string instruments and all open tube instruments. Remove spotlight. Wave speed is the one I want us to focus on this period. So wave speed, symbol V, measured in meters per second. That's what number 2 was about in the lab. This is how far the wave travels in 1 second. Wave speed is a rate. So there's actually going to be 2 ways to calculate wave speed. I could calculate wave speed by using the wave equation. I could still use it by doing distance over time. So if you want to fall back and do speed is distance over time, both of those are going to mean the same thing. You just use them in slightly different scenarios. So wave speed tells me maybe that it takes, I don't know, 2 seconds for a wave to travel 10 meters across the room. This would get me a wave speed of 5 meters per second. The 5 meters per second tells me how fast the wave carries energy across a space, across a distance. So one way I can calculate speed is distance over time. That stays the same. The other way is to use the wave equation. Now, weird thing about waves, okay? Really weird thing about waves is if I were to throw an object, like this cat. If I were to throw an object, the object would start at rest, it would accelerate, and then go at constant velocity, right? Waves don't do that. And listen up, because this one's weird. Waves, the moment they're created, are created at speed. They do not accelerate. They go from not existing to traveling at the speed that they're at, which is weird. Waves have no acceleration. And that's because the wave speed only depends on the medium you put it through. So if you were to do a wave on a slinky, for instance, like what we're going to do next week, if you were to do a wave on a slinky, it would go from not existing to traveling 15 meters per second instantaneously. Waves do not accelerate, which actually makes them mathematically a lot easier to deal with. They always travel at constant speed, as long as you don't change the medium they travel through. So the other way to do it is I can do wavelength times frequency. This is called the wave equation. If you know the wavelength and frequency, you can put them together to get wave speed. I actually really like this GIF because it shows these two waves on the top and bottom of this GIF travel the same speed. It's just that their wavelength and frequency are inversely related. So the one on the top is low frequency, large wavelength. The one on the bottom is high frequency, small wavelength, but they travel at the same rate because they're traveling through the same medium, the same material. So let me show you how to use this equation. I feel like this one's not a bad one mathematically, except that none of my animations showed up, so it looks overwhelming for a second. Ryan, I put a singer in here
Why?
because,
Wow.
okay, so let's say you're a soprano and you can actually hit a high C. I don't think I can, and we're not going to try because I like you guys.
Let's not.
All right, so a soprano sings a high C, and that has a frequency of 1046 hertz. The vibrations from the source in her throat are going to be vibrating 1046 times per second, right? Now, most singers sing in air. And because she's singing in air, we take the speed of sound in air, that's 340 meters per second, and I can work backwards and calculate.
343 meters.
I think 340 meters per second is at 20 Celsius. And 343 is at a little bit different temperature. We're going to use 340. If you need it for a test, I would give you the speed of sound, so don't feel like you need to memorize it. Okay. So she goes and she's singing, right? As that vibrations in her throat starts to shake the air immediately starts shaking, and it propagates at 340 meters per second. So I would put in V is 340. The frequency is 1046, and I could divide them out to get the wavelength. So the wavelength that she makes of the longitudinal wave in air is 0.325 meters. Okay, so let's say someone else comes along and they're going to sing the same exact note, but one octave lower. We'll talk more about what octaves mean later, but
It's
one
half the frequency.
it's half the frequency. So then a tenor comes along and he sings exactly 1 octave lower. That's half the frequency.
That's still a pretty high note for a tenor.
That is a pretty high note for a tenor. Yeah. So 523 hertz. So he's singing at 523 hertz. Calculate the wavelength. A common misconception that people have is they're like, oh, that must mean the speed of sound changed. He's singing a lower note, then the speed changes, right? No. The wavelength and frequency affect each other, but the speed's always the same. So if I put my soprano and tenor next to each other, they sing different notes, they have different wavelengths, but the wave speed stays the same. And if we really wanted to, you could put any frequency and wavelength as long as their product equaled 340, and that would be a sound in air. Okay. So what does wave speed depend on? You actually figured this out in your lab, but I didn't ask about it. Right? The speed of any wave depends on the medium it travels through. I don't know. So call out the medium for the waves you see that come up. Ready? What is the medium of this wave?
People.
It's a people wave. Ooh, so we said the medium is people. What is the medium of this wave?
It's hard to see what it is.
It's the thing doing the waving. What's the thing doing the waving?
Looks like a table.
Oh no, it's on the table. What's the thing doing the wave? A string or... It's actually a slinky. We will do slinky lab next week. So medium of this wave is a slinky, and the only way you can change the speed of this wave is to change some physical property of the slinky. Right? So in order to change the speed of a wave, you have to change the medium. What is the medium of this wave? It's an earthquake wave, the medium of which is the earth. The earth does shaking in the earthquake wave. And actually, if you watch the little animation of the house, so the P waves, the longitudinal waves, hit first. That shakes the house up and down. The S waves, the transverse waves, hit second. There's technically a third type called surface or love waves, named after a person whose last name was Love, not because we love surface waves, right? But an earthquake wave, the medium is the earth. If I do something like change the medium, change the density, temperature, pressure, material, if it changes phase from solid, liquid to gas, then that changes the speed of a wave. So for that, I've got a demo. Normally, when I make a sound, what is the medium that the sound travels through? The air. So if I could change the medium, then I can change the speed. So you notice that I have like these helium balloons here? I'm not gonna pop it. That'd be a waste of helium balloon. This one says happy birthday. All right, so.
You're gonna breathe it in?
I am.
Oh,
What is the difference between helium and regular air?
helium's less dense.
Less dense. And if you change the medium, you change the speed. Okay. So I've already used this balloon before. What I will say is, compared to other things, helium, when you breathe it in, isn't going to react to anything in your lungs. Helium is a noble gas. So when you inhale it, isn't going to do things like bond to your blood like carbon monoxide would. Right? But even then, I'm going to suggest not doing this at home because you need oxygen for your brain. Okay? A common thing that people do when they try to do this demo is they breathe too much helium, and it either will give you a headache or make you pass out because your brain needs oxygen for things like thinking and breathing. So I'm using a straw here that's going to puncture the seal on the inside, but let it be reusable so I don't have to buy a bunch of different balloons. And the trick is it's less dense. So I've changed the medium, which will change the wave speed. Right. So if you want to learn how to do this, there's a little hole here on the bottom of the balloon. You stick the straw in, and you're going to feel it change resistance when it pops the inside, I don't know, threshold? You'll feel it.
I don't know if I got it. Oh, I
Ah.
did. I definitely did. I have made the wave speed faster, which makes the frequency higher.
Fun fact, wavelength didn't change at all. Wavelength didn't change at all because that's based on the size of the instrument. Okay. But if I make the speed faster, that makes the frequency higher. All right, so one more time.
Can I record it?
I'm recording it anyway, so. Yeah, do the thing.
Hi, this is Baseg here, teaching physics. This is why things with high speed have high frequency.
Speed goes up, frequency goes up, instrument stays the same. And since helium doesn't bond with things in your lungs, it's relatively easy to get out of your lungs. It isn't going to do things like cause carbon monoxide poisoning, where carbon monoxide will like bond with your blood and lead to bad things. All right. So what would happen if somebody inhaled a gas that was denser than air? It was denser than air. What do you think, kids at home?
That was fun.
Denser to make it go slower.
Mhm.
So it would have like, would you sound deeper?
I would.
There's a gas that does that.
There's several. Okay, so let me go find the video. That is what is up next. All right. So I don't want to do this one personally because one, this gas is hard to find. And two, because it's heavier than air instead of lighter than air, even though sulfur hexafluoride doesn't bond with things in your lungs, it has full electron shells, so it doesn't bond. Because it's heavier, it's harder to get out of your lungs. And we'll let Adam Savage from Mythbusters do this. Right?
I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
Well, several factors is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
Sulfur hexafluoride, which is 6 times denser than air. I inhale some of that. And my voice gets really low, and somehow I'm still funny. It's scientific!
That's awesome. That's like he's so jolly.
He sounds like he could be the bad guy in like a Marvel movie. Okay, so all the speeds of waves depend on the material they go through. With sound, if you have a lighter gas, it's easier to go through because think light gases are less massive. So it's easier to move each particle and they can travel across the room faster. So that's pattern number 1. Light gases faster than heavy gases because lighter molecules are easier to move than heavy ones. So when he goes and inhales sulfur hexafluoride, he has heavier molecules in his lungs. Heavier molecules will resonate through the wavelength. The size of the instrument stays the same. Since the resonating chamber in his throat stays the same size, but the speed went down, the frequency also decreased. You can do this with hot and cold gases too. The problem is, if you were inhaling a really, really cold or really, really hot gas, that would probably be bad. Like there's temperature limits to what humans can withstand. Hot gases have a faster speed of sound than cold gases because hot gases means they're vibrating more. Hot gases are vibrating faster because they literally have more thermal energy. Last pattern, sound travels faster in solids than it does in liquids or gases, right? Really good reason for this. When sound has all the molecules right close together, let's say I have a steel or something like that, all those molecules are really close together. So that means as soon as one vibrates, it immediately hits the one next to it, and the wave travels faster. So if I had to make a ranking, and I'll use this image to help us out here. Solids are the fastest, so I put that as steel. That's up on top. Solids have the fastest speed, so fast that it already went through. Here, it's going to start over again in 3 seconds. Watch how fast steel goes versus water versus air. Denser materials means the particles are close together. So when they have collisions, they just hit one after another. Water is a little farther spread apart, so solids then liquids, but gases are the slowest. So actually, if we were doing this as a list, helium would be somewhere between air and water. Helium is about 990 meters per second. Cold air would be even slower than regular air. Hey, is there any medium where sound speed goes to 0? What can't sound travel through?
A vacuum.
A vacuum. A vacuum, not like a vacuum cleaner, like a vacuum in space. Cold air is slower than hot air because the particles are traveling slowly. Cold air, let's say this is like 300 meters per second. But a vacuum, right? Something with no molecules in it has no speed. If I'm trying to make one molecule hit another and there's no molecules, you get no sound. Which means all those like science fiction movies and like TV shows you've watched, like Star Wars, where they're doing like the massive space battle, should technically be silent because sound needs a medium to travel. If you have no medium, you have no sound. Which brings us to one last demo. Right? Let's go measure the speed of sound, or speed of light in the microwave. Okay. So first off, how can I say we're measuring the speed of light if I'm using a microwave? Right? What's actually going on here is that light is an example of an electromagnetic wave, and all of those waves travel at the same speed. Okay, we are making a medium of marshmallows. You want them like evenly spaced enough. You don't want to use big marshmallows here because I want to find where the hot and cold spots in a microwave are. Okay, so let us grab my medium. We're gonna put it in the microwave. And while this is going, I want to make sure to take these items out. I want it so it doesn't rotate while it's in here. The reason is a microwave actually works on resonance. So we've got our Play-Doh microwave. We're gonna let that go. This is gonna cook for about a minute. And while that's going, it's not gonna rotate. I want it to stay really, really still because this is making the same type of resonance pattern as the standing waves before. So if it makes high amplitude sections, are those gonna be sections that are hot or cold? Hot. And then there's gonna be cold spots where the molecules don't move at all. When the microwave puts forth its frequency of all microwaves is 245 times 10 to the 6th hertz. It's the resonance frequency of water. So as it heats up the water, oh, that's warm. Let's stop that now. All right. We're gonna see a pattern of hot and cold spots. If you want, you have knives. You can poke it with knives. So I want you to find the hot spots.
Right here.
All right. That's one. Find the next one. Yep.
Around here, I'd say.
Yep.
Over here. Mostly on this side.
Yeah.
but it gets cold right here.
Yeah, so you'll see there's some spots where like the marshmallows didn't melt at all. They're like totally fine. So what I want to do is measure the distance of one antinode. Can you measure the distance between two hotspots that are next to each other?
Yes. Centimeters or inches?
Centimeters.
Say about maybe, what is that?
6 centimeters?
8 centimeters.
All right.
That's my guess, from the 6 to the 2.
6 to 12 is how many
6 to 12 is
centimeters?
8.
6 to 12.
Six.
And so since all electromagnetic waves travel at the same speed, right? You could measure a microwave. You could measure a laser. You could measure an X-ray. You could measure an ultraviolet. You could measure a gamma if it wasn't incredibly dangerous, and you probably shouldn't interact with gamma rays, right? So as your microwave cooks your food, what it's doing is it puts out a frequency that matches the natural resonance frequency of water. So it makes the same standing waves that you and I saw on the lab. So the pattern's going to be a little bit different. It's got antinodes on each end. And when we do this, we know that every 2 antinodes was equal to 1 wavelength. All right, so if we measured that this, we said was 6?
Yeah.
Okay.
6 centimeters.
All right, so if we said this was 6 centimeters, then a whole wave would be how long? Would be 12. All right, so 1 wavelength is 12 centimeters. Let's add that together with the frequency of all microwaves. The frequency of all microwaves is 265 times 10 to the 6th hertz. Very, very, very high frequency. So it's going, what, 265 million cycles per second? And when that frequency hits water molecules, the water molecules vibrate. And the more they vibrate, the hotter they get, making hot and cold spots. And since this wave equation is true for all waves, whether they're transverse or longitudinal, that means we just measured the speed of light to be 0.12 times 265 times 10 to the 6th.
I believe it.
Yeah. Let's calculator that and see how close that is.
Is that meters per second?
That's going to be in meters per second.
It's going to be a big number, Mr. Sagan.
Oh, yeah, it is. It's 3.18 times 10 to the 8th meters per second.
Can you... What's 10 to the 8th?
10 to the 8th. So this number that we just measured is 318,000,000 meters per second.
It's not as big as I thought.
Right. It's about as fast to go around the Earth 6 times in 1 second. Circumference of the Earth.
Oh, never mind. That's pretty fast.
It's pretty fast. It's pretty fast. Technically, we didn't measure the speed of light in a vacuum. Technically, we measured the speed of light in a marshmallow, but that's kind of close enough. All right, so the real speed of light, when we use it, we're going to use 3 times 10 to the 8th. But again, just like speed of sound, don't feel like you need to memorize this number. You'd be given it if you need it. So speed of light is 3 times 10 to the 8th meters per second. Speed of sound is about 1,000,000 times slower than that, 340 meters per second. And you and I can run at about a maximum of 10 meters per second. Usain Bolt sprinting is about 10 meters per second. You have 2 assignments that are due. You can work on homework 9.1 or experiment 9A, whichever it is you need to work on right now. Work on homework and I'll be back in about 10 minutes or so.